The question that I have is, could you show examples on developing 2D free body diagrams? Now that we have all the fundamentals we need, let's go ahead and develop free body diagrams for some problems. Let's remember the key steps of developing a free body diagram. Number one, we want to define the body to be analyzed. Number two, we want to mark and label all the forces. Number three, mark the geometrical details. In this problem, it's kind of obvious that we want to analyze the beam, right? And therefore, the body to be analyzed is the beam AB. In some problems, it may not be this straightforward. Maybe structure is a kind of a complex thing, and you want to analyze a small part of that, right? So in that case, you definitely have to define exactly what is it that you want to do, and then define the body accordingly. We'll see later in the next chapter when we talk about the internal forces, we kind of run into the same problem. We're going to take a beam and section it and kind of divide that into two parts. Then you have to really define whether you want to analyze the left side or the right side. So this problem is fairly simple. The main thing here is the beam, and therefore we just want to analyze the beam, right? So here are my free body diagrams. In the first case, I drew the free body diagram right on the problem picture, which is this right here. And in the second one, I isolated the beam from the support and drew the free body diagram just for the beam. Again, because the problem is simple, either one is acceptable. You're not going to run into any confusions with either one of these free body diagrams. So as we go from the problem picture, all we had to do was to mark the support reactions and label them. So this is a fixed support, therefore we're going to have two force components, AX in the horizontal direction, AY in the vertical direction, and a moment MA. One of the common questions that I get from students is, why did I draw the horizontal force to be going from left to right, and why did I take the vertical force to be in that direction, vertically upward, and why did I take the moment in the counterclockwise direction? The answer is, the choice is arbitrary. You can take any direction you wish, because at this point, we don't really know the actual direction, right? After we solve the problem using the equilibrium equation, the numbers will tell you. For example, here I mark my AY to be vertically upward, right? And then let's say I go ahead and solve for AY, and it turns out to be minus 30 kilonewton. All right, so what does that mean? That means the direction that I have assumed here is not correct. It's actually other way around. It's in the negative direction. So likewise, the sign of any of these will tell you whether your initial assumption was right or wrong. That's it, as simple as that. Well, did I do this right? Well, I have identified the body to be analyzed, which is beam AB. And then did I mark and label all the forces? Yeah, this is the applied force, this is the applied moment, and I have marked and labeled the support reactions, right? Well, step number 3, mark all geometrical detail. Did I mark the relevant geometrical detail? Yeah, well, these lengths are the relevant geometrical details for this problem. I have marked them. So yes, I have all of the required elements in these free body diagrams. So it doesn't matter which one I use, I can write down the force equilibrium equations and the moment equilibrium equation just simply by looking at either this or this. So here's another example. So this is a little foot pedal problem. So here's your foot pedal, and here's the foot of the operator, right? He's applying a force on the pedal using his foot. And this is what we call a short link, basically a hydraulic actuator kind of thing. And here you have a spring. So this hydraulic actuator or the short link is also another two force member that I haven't talked about before. All right. So it's given that the operator applies a vertical force F to the pedal so that the spring is stretched 1.5 inches and the force in the short link at B is 20 pounds. And we are to draw an idealized model and the free body diagram of the foot pedal. So this is an example of a problem where the structure is kind of complex, right? So we definitely need to define the part of the structure we want to analyze. So in this problem, they have told us what needs to be analyzed, which is the foot pedal. So that takes care of the first step in developing a free body diagram, which is identifying the body to be analyzed, right? So here is the idealized model, and here is the free body diagram. So basically we are isolating the foot pedal from the supports. The foot pedal is connected to three separate supports here. This point right there through this short link, this point through this spring, and of course this plane through a pin. The short link and the springs are basically two force members, and therefore the direction of the forces on those members are going to be in the direction of the members themselves. So the force on the short link is going to be horizontal like that, and the force on the spring is going to be horizontal like that. When you apply a vertically downward force on the foot pedal like shown in this picture, you can see that the hydraulic actuator is going to be resisting that, and therefore the 20-pound, the force on the short link is going to be pulling the foot pedal in that direction. And the spring is going to be extending, right? There's going to be an extension on the spring, and therefore the force on the spring is also going to be in that direction. In other words, the spring is going to be pulling the foot pedal in that direction. The magnitude of the force in the short link is given, 20 pounds, so we just mark that over there. And the magnitude of the force in the spring is not given, but they have given us the spring constant K and the extension on the spring, which is 1.5 inches, right? So we use those two numbers in this equation and calculate the force on the spring, which is 30 pounds. Now this is a pin, and therefore there could be two forces, one in the horizontal direction, one in the vertical direction at that pin. Again, you don't know the directions at this point, so you can mark them in any direction you want. So here I have marked the vertical force in the vertically upward direction and the horizontal force in the direction going from right to left. Okay, so we have identified the body to be analyzed. We have marked all the forces and labeled them, and we have all the geometrical details, which are these dimensions. So this is a complete free body diagram. Here's one more example, and we want to develop the free body diagram of the smooth pipe, which is this pipe right there, which rests against the opening at points of contacts A, B, and C. Here's the solution. The body to be analyzed is given to us, and in this case I have chosen to draw the free body diagram right on the picture. The pipe is supported at 3 points, point C, point B, and point A. So it's given that the pipe is smooth, and therefore we have to assume that these contacts are smooth. When these contacts are smooth, these supports behave like rollers. So at contact C, the pipe can move in the horizontal direction effortlessly, and therefore there is no force in that direction. But it cannot move in the vertical direction, right? And therefore there is a force there, Fc. This is simply a point contact, and the pipe can rotate if it wishes to do so. And therefore support is not applying a moment, and there is no moment at that point. So in terms of mechanics, this contact is similar to a roller pipe arrangement like shown over here. A similar situation over here, right? So the pipe can move in the horizontal direction effortlessly, and therefore there is no force in that direction, but it cannot move in the vertical direction. So we do have a vertical force, and there is no moment at point B. Point A is similar, but it could be confusing to some of you. So the easy way to figure out the direction of the force at that point is to first see which way the pipe can move effortlessly. Now you can see this pipe at that point can move easily in that direction, right, on that plane, right? And therefore this contact is similar to a roller like this. So we have a zero force in that direction, but non-zero force in that direction, and there is no moment. As part of marking all the geometrical details, you also want to mark the direction of that force. You might say, well, I'll try to figure it out when I do the problem. Well, that's not good enough. Defining the direction is part of developing the free body diagram, not part of doing the problem. So direction is pretty straightforward. This line makes an angle of 30 degrees, and this force is parallel to that line, and therefore this force also makes an angle of 30 degrees to horizontal. So that's all you have to do. Since we are drawing the free body diagram right on the problem, picture all of the other dimensions already there. So that's it. So that's a complete free body diagram. I cannot emphasize the importance of doing this right. For example, since we have done this very carefully, we have introduced three unknowns, right? FA, FB, and FC into the problem. Remember, we can write down three equilibrium equations. For example, two force equations and one moment equation, right? So three unknown, three equations, we can solve for the unknowns. But if you didn't do this right, you might have introduced four unknowns or five unknowns, but you can only write down three equilibrium equations. So you would think this is a problem that cannot be solved, which is incorrect. Let's go one more example. In this problem, we have a bent pipe. Applied forces are given. We have a vertical point load of 100 pounds. And we have a concentrated moment of 200 pound-foot acting at that corner. The pipe is supported on a smooth surface at point B and by a collar at point A. The question is to draw the free body diagram of this bent pipe. So the body to be analyzed, once again, is defined in this problem. I'm going to draw the free body diagram right on the problem picture. So the pipe is supported at 2 points, point A and point B. So let's go ahead and develop the forces at point A first. So this is a collar that is free to slide in that direction. Therefore, force in that direction has to be 0. But there has to be a non-zero force in the direction perpendicular to that supporting arm. Let's call that as FA. This part of the rod is welded to the collar at this point. You can see that, right? And therefore, there has to be a moment. I labeled it as MA. Marking this in the counterclockwise direction is just my choice. And same thing goes for this too. Marking the force in that direction is my choice. You can mark it any way you like. We have a smooth contact at point B. So you can see the pipe can slide in that direction, right, effortlessly, and therefore the force in that direction has to be equal to 0. But there's going to be a force in the direction perpendicular to that. So let's call that as FB. And on a point contact like this, there will not be any moment. So we have finished marking the support reactions. There are three of them, FA, FB, and MA. We can write down three equilibrium equations for this problem, and therefore this problem can be solved. We are not done yet. Now we want to mark the directions of the forces FA and FB. Let's take FA first. The direction of this line is given as ratios, right? 3 horizontal to 4 vertical. This line, the line representing the direction of FA, is perpendicular to this line, right? So it turns out that the ratios of this line can be obtained from these ratios simply by switching the horizontal and the vertical ratios. In other words, you take this vertical side, right, which has a ratio of 4, you put that on the horizontal side here. And you take this horizontal side and put it on the vertical side. The hypotenuse remains the same. And this can be easily proved like shown over here. Say I draw two perpendicular lines like this, right? So like in this example, let's say the ratio of this line is 4 vertical to 3 horizontal, and therefore the hypotenuse is 5. If I call this angle as theta, this little angle is theta, and therefore you can see sine theta is simply 4 over 5, right? Now if this is theta, then we know this is 90 minus theta, this angle will be theta, and therefore this little angle is theta. So if I switch the vertical and horizontal sides, and you can see sine theta still works out to be 4 over 5, right? So this is a general result. So anytime you know the direction of a line, you want to find the direction of a line that is perpendicular to it, all you have to do is to switch the horizontal and the vertical sides if the direction is defined in terms of ratios. The same technique works here as well, because this line is perpendicular to that, and therefore all I have to do is to switch the ratios. So I take the 5, which is on the vertical side over here, and put it on the horizontal side over here. And I take this 12 and put it on the vertical side. The hypotenuse remains the same, 13. Now my free body diagram is complete.